The hypergeometric distribution is similar to binomial distribution, but with a slight difference. In binomial distribution, the Bernoulli trials, meaning number of experiments performed, are independent, but in hypergeometric distribution, they are not. This means that the probability of success in one trial will affect the probability of success in the next trial. But like the binomial distribution, each trial of hypergeometric distribution can have only two outcomes, 0 or 1, where 0 represents failure and 1 represents success. Mathematically, the probability mass function of the hypergeometric distribution is defined as follows. Here, capital N represents the population size. This is basically the total number of elements in the sample space. Capital K represents the number of success states in the population. This means the total number of elements in the sample space that are considered as success when sampling. Lowercase n represents the number of draws. This is the number of elements that we will draw from the population. Lowercase k represents the number of observed successes. Note the difference between capital K and lowercase k. Capital K is the total number of success states in the population, while small k is the number of success states in the sample drawn. P of x equal k is the probability mass function of the hypergeometric distribution, which gives the probability of k successes in n draws. Let's try to get the intuition behind this formula by proving it using combinatorics. As we know, we have n items in the population, k of which are success states. This means n minus k items are failure states. Since the sampling is done without replacement, the number of ways to choose k success states from total success states can be calculated using the binomial coefficient like this. Also note that we need to have exactly k success states in the sample. This means if we are drawing n times, we will need to have n minus k failure states as well. Total number of ways to choose failure states can be calculated using the binomial coefficient as well, like this. Using the multiplication rule, we can calculate the total number of favorable outcomes for exact k successes in n draws. If you are not familiar with the multiplication rule or binomial coefficient, I would recommend you to watch Chapter 3 and Chapter 4 of this playlist. We have covered these topics in detail there. Total number of outcomes would be capital N. Choose lowercase n as we are drawing n items from a population of size n. Now, by naive definition of probability, the probability of k successes in n draws can be calculated by dividing the total number of favorable outcomes by the total number of outcomes. Substituting the values of total favorable outcomes and total overall outcomes, we get the probability mass function of the hypergeometric distribution. Let's take an example to understand this better. Suppose we have a box with 12 balls, 5 of which are red and 7 are green. And let's say drawing a green ball is considered a success and drawing a red ball is considered a failure. Our population size in this case would be 12, as there are 12 balls in the box. The number of success states in the population would be 7, as there are 7 green balls in the box. And let's say we are drawing 3 balls from the box. Therefore, the number of draws would be 3. Now let's say we want to calculate the probability of drawing exactly 2 green balls. This means we want to calculate P of x equal 2. Therefore, number of observed successes would be 2. Substituting these values in the formula, we get the probability of drawing exactly 2 green balls as 0.4773. Similarly, we can calculate the probability of drawing all other possible number of green balls. To see the distribution of the probability mass function, we can plot the probability of drawing each number of green balls like this. I hope this video helped you understand the hypergeometric distribution. With this, we come to the end of this video. If you like this video, make sure to like, share and subscribe to the channel. In the next video, we will learn about the uniform distribution. Thank you for watching.